Yeah, so hi everyone. I just wanted to make a quick announcement about our new causality for time series reading group. We've been doing it for a couple weeks in person at UBC, but we are going to start doing it online. So if causality and time series interests you, which I'm sure it does for many of you, then click on the link that I'm sending in chat and add your name and yeah, we'll send you the information for it. It's on Fridays, so Friday uh, at lunchtime. So, thanks.
Every Friday?
Yes, every Friday.
Okay, thank you.
Okay.
Perfect. Go on. Hi. Yeah, Joseph, thanks for sharing that. I'm also at UBC, and I haven't met you yet, but I look forward to doing that soon.
Yeah, we have lunch at in the Earth Science building, so you can come by and we can talk.
Great. Sounds good. Let me share my screen here. Needs to be enabled participant screen sharing, please.
Okay, you are the co-host now
Okay,
then.
thanks. Okay. Yeah, nice to see everyone. Thanks for joining today. I was really excited about this paper a while back, and like usual, I get really excited, and then the more I dig into it, the more I realize the nuance and how much I don't know. I think this idea of looking at models in the lens of compression is really interesting. I'm not an LLM expert or neural network expert, but definitely after going through this, I've learned a lot about kind of some of the inner workings, and yeah, I think to start for a bit of motivation, I might link the idea or this human knowledge compression prize. I want to describe it a little bit because there are connections to the paper that we're going to discuss. Again, the paper is Language Modeling's Compression by Delatang et al. And then we'll jump into the paper, kind of start, not really go in the order that's presented in the paper. I'm going to try and keep the presentation to maybe 20 minutes. I made a Manim video to help myself understand the arithmetic encoding algorithm, and it's kind of central to this this duality or the equivalence of language models as predictors, general predictors, and compressors. So I don't want to go more than say 20 minutes. I have 25 slides. I don't think I'll take a minute per slide, but I want to share, just kind of step through this this animation afterwards, and maybe hopefully that will promote some discussion about kind of about the nuance in this topic. So we'll start with the data and models, and then go to results, kind of like going from very general to more specific, and then getting into some of the kind of key concepts from the paper, and then use that as sort of an introduction to or as a segue to introducing this idea that I've spoken with Hoshin about, and with Stephen, my supervisor at UBC, about kind of taking the same idea of the human knowledge compression prize and maybe applying it to earth science data. So the human knowledge compression prize was introduced in 2005 or 2006 by Marcus Hutter. And if you go through the author list in the paper that we're looking at today, he's one of the authors. He's a co-author. So it was a collaboration between I think Google DeepMind and another kind of big research group. Knowledge compression prize basically he posed this task, which is there's a reference text and it's a string. It's a plain text or Unicode string, and it's 10 to the 9 bytes long. And the task is to compress it using minimum description length principle. The reference text is it's this NWIC9 short form here represents a snapshot from March 2006 of Wikipedia. So it's not just it's not just text kind of strung together from Wikipedia. There is some structure to it, and I'll show you what that looks like in a bit. And there's a cash incentive offered for improving compression. So there haven't been that many winners. It's been around for getting close to 20 years now, I guess 18 years. There have been sort of two forms of it, and really the difference between these two tables is around between 2017 and 2019. They changed the rules a bit to reflect maybe the realities of consumer grade computation. So in fact, like 5 days ago, there was a new winner declared. So that 1 gigabyte string has been reduced to 11.2% of the original uncompressed size, and that was by this person Kaido Orav. And for doing that, almost 7,000 euro were collected. So how do you compress human knowledge? So you go to the contest website, you get the reference file in a zip form. It's about 320 megabytes. When you expand it, when you extract that archive, it expands to that original 1 billion byte string. You develop an executable compressor. You use that compressor to compress the byte string, the original standard string, into an executable archive file. You demonstrate that the archive file losslessly replicates the reference text, the NWIC9 reference text, and then you show that the size of the compressor plus the archive is less than 112 megabytes, which corresponds to this current lead, which was set 5 days ago. And for every 1% improvement you achieve over the current best, you get 5,000 euros. So that's the incentive. And here's our winner on the left side. So what does it look like? So if you just view the first, say this is the first 1,000 characters, it's actually an X format, which it's not, the written content, it has structure to it, and that makes it machine readable. And I guess that has other implications for how a machine can learn from it, with structure like assigning certain keys to words, right? So you can link, say, blocks of text with certain headings, kind of thing. So this text string, this reference string, has far fewer symbols than can actually be encoded in UTF-8. It has only about 11,000, which is a huge number, but it's quite a bit smaller than what it could be. So why the Human Knowledge Compression Prize? There's, kind of like, I guess, compression is used in day-to-day communication and computation. Working in compression both requires and yields understanding. So it's sort of a feedback loop between learning about data, learning about like fundamental aspects of data, and from that, creating better compressors. There's a loop between creating better predictors and compressors. I'm not sure I can quite justify that duality, but compression enables prediction. And I think one of the, between advancing the state of the art for Marcus Hutter, the sponsor of the compression prize, is really advancing towards an AGI. So stepping into the paper, sorry, I'm doing this with PDF form. So stepping into the paper now, at the very highest level, it compares sort of two different approaches to compression. One is the classical compressors that we use day to day in our computer systems, for regular files, for images, for audio, for video. These have very small programs relative to the size of the data. And these classical compressors are optimized for sequential dependencies. And then in contrast, large language models are much bigger programs. They are optimized for rapid adaptation to changing contexts. Oops. So what do they do in this paper? They take 3 different input series from very distinct data source or modalities. They take an existing large language model, and that is one that's trained offline, so they don't modify it. They use the parameters that it's been trained with. They use that offline large language model to recover the coding distribution from the various input data. They apply arithmetic encoding to compute the minimal expected bit string length, which represents the compressed description. And then when you compare that compressed description, when you get your compression, you compare how the large language model, which may not be trained on specific data, to classical compressors, which really are doing something specifically. And in some cases, they're optimized for very specific applications like audio and video. So the 3 data sets that they use to test, to compare the different approaches. The first one is the same snapshot of Wikipedia that is used in the Hutter Prize. And so it's important to note here that the classical compressors like gzip, I think the sort of evolution of them, the improvements on some of the newer compression, an older classical compressor might not have been trained directly on something like Wikipedia, but it's trained on files that might be similar to XML. So it's not really in context, or in sample. But for the large language model, like the chinchilla model that they is one of the models, we'll get to that in a couple seconds. Definitely this is in sample. The second data type they look at is ImageNet. So ImageNet is 14 million images with annotations. So in order to get it into a format that that's comparable to the text of NWIC 9, basically they take patches of images in the sequence they appear in the image set, break them up into 32 by 64 patches, so that they break it up into these 32 by 64 patches converted to grayscale, so they can be flattened to produce basically 2 gigabit chunks, and that's so that it relates to the context of the transformers that they use and the large language models. And then basically take a 1 gigabyte string from the ordered image patches. And then similarly for the third data source, Libra Speech, this is 16 kilohertz English speech, and it includes 1,000 hours from audiobooks and different sources on the internet, and these are segmented and aligned. Similarly, they take sample chunked into 2 kilobit batches, and then flatten these out so that the result is a 1 gigabyte string. So the models compared. So we have these four at the top represent classical compressors. The first two are kind of general file compressors. The third is image. The fourth is kind of state of the art for audio. The program size of these classical compressors is in the order of megabytes. I actually just downloaded the gzip, the latest version, and I uncompressed it, and it's I think 5.8 megabytes. So compared to the 1 gigabyte file size, that's less than it's about 0.5%. So it's very small. Whereas as we go down here to the neural network models, we're increasing in the complexity of the model. So these values at the right indicate the number of parameters, and parameters are encoded in. So each parameter is 2 kilobytes. So the program sizes are then proportional to the number of parameters here. And these are generally for sequence prediction, but they can be converted to compressors by combining arithmetic encoding for lossless compression. So going into some of the results in general, for the Wikipedia, for the text or the snapshot of human knowledge, we can see there's two different columns here. The first one is the raw, and the second is the adjusted on the right. The raw compression is not taking into consideration the program file size. So if we don't consider the size of the model of the LLM, the largest LLM produces the greatest compression. But if we adjust for the number of parameters, it's by far the worst. Oh yeah, sorry, it's 2 bytes per parameter. So moving to the ImageNet, it's really the same. I think they specify, or they explicitly say that the chinchilla, there is an appendix where they describe what data sets the chinchilla model has been trained on, and I believe ImageNet wasn't a part of that. So this is definitely out of sample, and we can see that it beats the PNG, which is a domain specific compressor for images. So it beats it by quite a bit. But then again, once we adjust it for the model size, it's nowhere close. And then finally for Libre speech here, the same story. So FLAC is the lossless audio codec, free lossless audio codec. And you can see the difference between the raw and adjusted is there's no difference because the overhead of the program description is basically negligible. But the LLM vastly outperforms it in raw compression. And then I guess as a baseline, just to show that these are in fact incompressible with all these models, you could see that all of these numbers are greater than 100. So I show that as well. Okay, so I'll go through kind of 6 main points, and then I think we'll illustrate we'll walk through this arithmetic encoding example together to kind of maybe spur some discussion about what's going on here. So the sort of generalizing power of large models should also make them very good universal or general compressors. in order to kind of guide large language model development, they argue that prediction problems should be viewed as compression problem. The compression, sorry, the encoding, it doesn't take you very long in getting into discussions about or reading up in discussions online about, well, why restricted to loss encoding? Why not allow lossy encoding? Because we, our human brains forget things, but we do things very well. It's sort of, they make the point that this is sort of irrelevant, and really the compression only depends on the capacity of the probabilistic model. And that's something that I got a much better appreciation for going through this. 3 more points. Larger models compress better, but there is an optimal model size that is dictated by the data set. And they show a few, they show that the scaling laws are really a function of the data that we have to train it. The context length is the key to many problems. For things like logic, for math, we need to have much longer context. So these are not suited to large language models, which again are optimized for shorter contexts. But the classical compressors, some are, I guess, considered to have sort of infinite context. And large language models are trained on tokenized or compressed input. So they're not just trained on the raw bit stream, the raw symbols, the raw input. They are tokenized using things like byte pair encoding. So looking at the frequencies of pairs or multiples of symbols to improve efficiency and performance. So to highlight that first point, there's a really one of the papers they cite had evaluated the performance of GPT-4 on a bunch of different applications or types of problems, and it's sort of state of the art in a vast and growing number. For instance, here this is an example of it basically owning the Amazon kind of preliminary interview code skill test in a few minutes. So large language models are predictors. They predict the next sequence from the previous X symbols. To convert them to a compressor, to convert an LLM to a compressor, we recover the conditional distribution of P for all messages, and that's sort of all permutations of the dictionary or the vocabulary. So I think this will be illustrated much better in the animation. Basically, the length, this script L represents the encoded length of a sequence or a message, and then the conditional probability of a symbol given the preceding symbols that reflect the length of the context is recovered through this relationship. It's just the length in bits of a message encoded in arithmetic encoding, and then that's we'll get there to the next step. So there's another equivalence here, and that's with the expected message length of an optimal encoder. It's limited by the negative log likelihood of the model. So we don't usually have the true distribution, so we are approximating it with some parameterized statistical function, and reducing this expected the expected length is equivalent to minimizing the log loss or maximum likelihood. So this figure explains, they use this the paper to explain the process or the algorithm of arithmetic encoding. And it's sort of intuitive at first, and then when I to get into the details of, okay, I can understand sort of these steps, but how does that relate to the bigger picture? How does that relate to how a large language model can be converted to a compressor? I realized I didn't really understand, so I created this animation. I need to change this over. Okay. Okay, so yeah, feel free to stop me at any time to kind of go through some of these steps. So the example they provide in the paper is we're given a 3-symbol alphabet. It's the vocabulary is size 3, and we want to encode this message AIXI, and it's related to Marcus Hutter's AGI that he has named and developed. So we're given a coding distribution, and this is the first step of the coding distribution. The marginal probabilities of each of the individual, of each letter in the vocabulary. So on the left here, we break up. This rectangle represents the cumulative probability. All we're doing is we're breaking up this interval of 0 to 1 into more refined segments so that we have unique descriptions in encoded in binary, and that's shown to be optimal. So we get this first observation. It's an A, so we have our marginal probability. We set our first bit to 0. We go to the second step, and we take the interval that the marginal probability of A occupies, 0 to 0.45, and we break that down based on the first conditional probability. Again, assigning equal probability of the next bit being a 0, 1. So this is the first conditional model. We compute the cumulative probabilities within that interval. We have our second symbol in the message is an I, but we can't tell from this observation yet whether the second bit will be a 1 or a 0, so we have to go to a third bit. So we break that interval of 2 bits into 4. That interval of 2 into 4. And we compute the cumulative probability in that interval. We get our third symbol in the message, and we assign it we can now assign this 3-bit string to this conditional probability. We again bisect that interval on the left and compute the conditional or the cumulative probabilities within that segment on the right. And now, so given our last symbol, we can't assign this this bit string because it doesn't uniquely describe this marginal distribution. So we have to keep going. And we have to keep going a couple more times until we have a segment that falls within that margin. So this is the encoded string of the original message AIXI, and its conditional probability is 2 to the power minus 7. So we do that with all combinations of messages given this dictionary, and that's how we compute the log likelihood. And for this particular message, we have about 22%, right, 5 times compression factor, or 22% of the original length. Are there any questions about that? So this to me is really where I get an intuition of where the law occurs. You know, we have a conditional model, and we have a conditional model with a context length of I guess that's 3, or maybe it's 4. I think we have to get down. We have to get back here to really see. Yeah. So we are predicting. We're given the model that we have predicts the next string based on at most the last 3 symbols. Sorry, the next symbol on at most the previous 3 symbols. So I guess that's a context length of 3. But even then, even with a very small vocabulary and a very small context, the complexity is large. So developing this conditional model requires a lot of training. And I guess the loss in, or the negative log likelihood loss is really a function of how well these more distant conditional probabilities are approximated by the data that we have to train. Does that make sense?
Yes, and this is a great example.
Okay. Okay, so I'll come back from that. I'll leave this up in case want to come back to it. And I'll share this again. Okay, so we're back here. Okay, last few points. This is a point about the scaling laws. So I've read.
Actually, I do have a question, Dan.
Oh yeah, go ahead.
So this is based on the idea of binary encoding, correct? You're trying to figure out how many bits, but you do that with this partitioning into every time you break it down into 2 halves, correct?
Yeah. So
Yeah.
I guess arithmetic encoding is binary encoding.
Well,
Maybe I shouldn't.
I was just going to suggest that you could even do ternary or anything, because it's just a matter of at every step whether you do a partitioning by 2 or 3 or 4, right? So it's general. That was my question.
That's, yeah, I didn't think that far ahead. And I'm not sure how that would, how that would affect this. Yeah, would it be a trade-off somewhere?
Oh, I don't know if it I don't know if it makes a difference in terms of information, but in terms of representation. So here you're representing zeros and ones, but you could do, which means you're reducing it to a binary language, but you could reduce it to any other language. Am I correct, Stephen?
Yes, I think it's just basically a binary expansion of a fraction in this case, which gets you this interval in probabilities where you are at. But that can be any kind of, that doesn't need to be binary. It can be any number system.
And you have to go to 7 bits in this example in order to get a perfect representation. But if you stopped at 6 bits, you would get some kind of approximation, correct? And so on.
Yeah, and I
Yeah,
guess that's, oh, sorry, go ahead.
Yeah, I guess then you would end up with a probability distribution over the last character.
Yeah.
And I guess we can also see that the 7 bits is not fully efficient because the little probability interval we end up with is quite a bit smaller than the actual condition probability of that string.
Right.
Right. So in some cases, if you're lucky, those are much closer together. So there's less loss.
Okay.
Because basically we have to round to an integer number of bits, right?
So you would say it's optimal binary, but if ternary gave you a better representation, you'd have a different, you'd have a
That might, yeah, that might actually be.
Symbols. Yeah. Okay.
But it's already a big improvement compared to like Huffman coding, which works character by character. Because there, if the probability of one character is not exactly a negative power of 2, an integer negative power of 2, for each character you have this overhead.
Mm-hmm.
But here you basically encode the whole string into one number. So the overhead is shared between the whole string, basically.
Mm-hmm.
So that makes it somewhat more efficient than Huffman coding.
Thanks for going through this, Dan. I'd seen it before. I kind of understood it the first time. I still don't claim to completely understand it, but it's nice to see it over and over again.
Yeah, I think it's very convenient when you have a compressed bit string to take each message and simply get its conditional probability by, from 2 to the negative of the length, negative power of the length, right?
Mm-hmm.
That seems quite simple.
Yeah. And then to decode it, you just read from the right. Did you go through the decoding process?
Yes. So decoding is, I think it's actually from the left.
You still have to read from the left. Okay.
Yeah. And I think at some point I had it in my head, but I'm
okay. I don't want to get sidetracked on this because
okay.
I know you have a bigger story to tell. Yeah. Okay.
Back here then. Okay, so coming back to the scaling laws, this tendency of these language models to become bigger and bigger. Really, it's the justifiable size is dictated by the data set. If we have an infinite data set, the internet, the corpus of the internet is immense, so we can justify having a very large model in order to work on many different modalities. But even then, I think they talk about being in the order of many bytes to justify such large models. So the idea is that at some point the model size is really the model is ineffective at reducing the entropy of the conditional distribution. So we can see here, this is the adjusted compression rate for these three different versions of Wikipedia. They are 7 to 9, basically goes in order of time and also size of the data set. I think the 8 version is it 100 megabytes, going up to a gigabyte for 9. So for the second two, you can see that there's an optimal model size expressed, but really the first one is too small to justify any of the models that were attempted. And these are transformers, sort of they call them vanilla transformers, trained on some part of, I think it was trained on this first version, so a very small part of it, using the context length of 2 kilobytes. So coming back to this point that context length is the key to the problem. So this highlights the two different approaches. Classical compressors, some have context lengths in the order of tens or hundreds of kilobytes up to infinite. I don't understand the interpretation of how a compressor could have an infinite context length, but transformers are very limited by this, and that's because generating this conditional model is, I guess, expands geometrically. So you add one level, add one symbol to the context, and you are increasing your complexity geometrically. Again, we can see this difference in, so the LZMA gzip compressors, the classical compressors, the compression rate comes down quite rapidly at the start, but it's really the large language model that learns much faster. So the faster this decreases, with the increasing sequence length, that's how effective it is at learning what's coming up, like learning from the new information in the sequence. And it's the same across modalities. So the same pattern is exhibited, except for this smaller transformer, which hits a wall very quickly in the ImageNet and Lever speech. So the other concept is tokenization. So these are not, large language models are not just trained on the raw sequence of symbols. They are, that raw input sequence is tokenized first. And that describes this trade-off between the vocabulary size and where am I here? There's the model size and sorry. Where am I? Okay, let's start on the left here. So the tokenization, the ASCII at the top is essentially no tokenization. Its ASCII is just 256 symbol vocabulary. And then byte pair encoding. By doing byte pair encoding, we can then find frequent combinations of symbols, and then increasing we can increase the vocabulary that way, and that increases the information of the encoding. And on the top here, these are different size models. So a small transformer to a large transformer. We see that the larger model benefits from, doesn't benefit from tokenization, while the tokenized model with a much larger vocabulary does benefit, with a smaller model benefits from a bigger vocabulary. Okay, so coming back to how this relates to prediction in geosciences, I was really inspired by Julie Mai's work with the Great Lakes Runoff Intercomparison Project. I think there's a big parallel here. You know, they compared you know, a wide variety of model approaches, and they used I don't think KGE was the unique metric they used, but it was one metric. And this other work, this language modeling is compression work, and this Hutter Prize, it sort of raises the question, well, can a similar contest be done using minimum description length as a So that's when, yeah, discussing with Stephen and with Hoshin, this idea of the hydrological knowledge compression or Camels compression challenge or prize. You know, can we format, say, a reference data set such as Camels into a format similar to the way that this other study or other studies have done into a 1 gigabyte string? Standardize the baseline data in terms of time series of observed hydrometeorological data, limit the number of parameters, and the details, the really difficult details are defining the submission criteria. So the human knowledge compression prize requires the delivery of these executable files. They have to be executable on Windows and Linux. That might limit participation. So figuring out the submission format, and B, kind of computational limits that are set. So there's a time limit and there's also a memory limit in the human knowledge prize. And those limits really exclude large language models. But some of these ideas, yeah, still need to be worked out to really present it and open up this challenge and encourage people to participate, and maybe facilitate some of that through assisting with like creating executables or providing codes to do so. Yeah, that's all I have for this today. Oh, there's a hand raised.
Oh yeah, thanks, Dan. That was a great talk. And I'll have more questions if there's time. But the first one, so in that computation limit, then, is the training of the model included in that sort of computation limit, or is that something that could be external? You pre-train a model, but if you can load it and sort of run the compression algorithm within some stricter limit, then that's okay.
Yeah, so I mean that was the point of I didn't get into the online versus offline. They strictly use the offline scenario where okay, this large language model has been trained elsewhere. It's been trained on the internet, and so you don't have to train it. It's already a general compressor, so you don't have to train it, and you don't include that. That's already been done. That answer that anyway?
Yeah, no, that's really helpful. And I'm just again spitballing here about how you might structure a competition, but one thought that would be sort of fairly accessible would be that your model has to, first of all, it has to be available on the internet so that someone can download it. And then you'd have to run your compression, say, on a GitLab runner, or sorry, a GitHub runner, which sort of gives you, you know, fairly stock, I guess sort of a stock configuration and environment. It's fairly constraining, but it should be more than adequate for running a compression with a pre-trained model. And to accomplish that, the model would also have to be available for download so that your GitHub instance or whatever instance you're running would be able to download it and run it.
Okay. Yeah, I guess it depends on the approach. So one approach could be to use a pre-trained model. But as this paper has shown, they are sorry, if I come back here, if the adjusted column here, the adjusted compression, that takes into consideration the model size. So really, these large language models are not going to compete. They don't compress once you take into consideration the parameters. So the model is up to the participant, and it can be as simple as a program that says take the previous value, or take a run mean of the previous values. And if that provides any compression over the raw file, then that's a viable model. But I think the trick is getting from something like an R script or a Python file or a Bash script into an executable. I mean, that maybe is somewhere where there could be more information or more help provided.
Yeah,
from a
exactly.
content structure.
And I think, some of those sort of simple compression tricks that you described, they are baked into some of the standard algorithms, but I also suspect that over the past decade or so, we've gotten a little lazy because it's been very cheap, like on HPCs and stuff. And so people have stopped using them and maybe neglected them a little bit. So this will be a fun challenge for sure.
Layla, did you have your hand up?
Yes, I have a question. And first of all, thanks, Dan, for introducing us to this paper. It's really good. And I really enjoy the comparison between the different compressions for different models and how they treated different data sets. So my question is related to that, the data sets in the different type of data. So my question is about the biases that might be unique to each type of data, and how do you think that different modality affect the compression performance? Because that is usually what happens with the data that we have. We can have time series data or satellite data, and we will try to compress the maximum amount of data. And so I guess, yeah, I'm curious, what do you think about the biases that are unique of that data? How it will affect the compression performance?
Yeah, I guess so reading through some of the human knowledge compression submissions, or the descriptions and the discussions around those, I think what people do is they apply a bunch of different things. These very general compressors, the gzip, they really take advantage of sequences, and yeah, neural networks can't do that because they don't have the context length to capture sequential dependencies to the same extent. So I guess bias would be where, yeah, in an approach could be the extent to which it could, one way would be the extent to which it could, what would you say, exploit sequential dependencies. It just, does that, I don't, yeah. Did you mean like anything specific, any specific biases?
No, not really. It's just I was wondering how different are the nature of each of the measurements, and I was thinking like I don't know, because in the paper they say when they describe the data sets that they render the results comparable across modalities by limiting all the data sets to 1 gigabyte. So I was
Yeah.
wondering how limiting the amount of data that you're going to be using for each of the different modalities is going to make the results comparable.
Yeah, and I think also just the way that the image data set was kind of transformed for the purpose of making them right. It was, they are RGB images, but they were converted to grayscale so that each so that one pixel could correspond to one chunk or one context length.
Yeah. Mhm.
So yeah, I'm sure there's something there. If you take out the color information, you're losing information there. Yeah.
Right. Thank you, Dan.
Thank you. Hey, Joseph.
Yeah, thanks. So in a way, hydrologists have been kind of doing this compression challenge for a long time through
Mhm.
hydrological signatures. I'm wondering if you've looked at kind of the lossiness of how well, all the hydrological signatures we've developed in the past, I don't know, 20 years, how well they kind of correspond to the original streamflow time series. Have you looked into that at all?
Yeah, I guess that's maybe the underlying question of any modeling, or maybe like looking at specific ones. No, but yeah, I guess the point of having a very large model is to to not restrict to particular ones that are lossy models, and to I guess allow for adaptation in the short term. That's a very good question.
Yeah, because it kind of it could lead to better hydrological signatures. Like there's some information that, in the streamflow time series that we're kind of missing every time we're looking at hydrological signatures instead of the actual time series.
Yeah, so one thing I didn't present in this is that was in the paper. So they flip the compressors, the classical compressors, around and use them as generative models. So, compressing the data string and then computing the length of messages within the context, within that 2 kilobyte context, and then using that to generate, say, an image or a string of text given a prompt of 1 context length. And I think that's one of the key points is that going backwards and forwards, you kind of learn about one from the other. I don't know if that makes any sense. It's sort of an impression I got that looking at the way, looking at how the say images are generated from gzip compared to predicting sequences, the next sequences in the image using the chinchilla model, they're different. And so I think that could be analogous in some way to looking at how they map to signatures.
Thanks.
Stephen, did you have your hand up?
Yeah, I was wondering for the compression challenge, you mentioned that we should have some meteorological data available for the model, so that can then become towards the size, I suppose, right? Because I think you can kind of have several competitions. Like one would be just to compress the Camels streamflow series, which means you're trying to basically find signatures that describe the streamflow itself very efficiently. But then if you say, like, I have this chunk of meteorological data available to pull from without penalty in your compressed length, then you're doing rainfall modeling basically. And then if you have like all the different streamflow signals, places and catchment characteristics available, you're kind of converting it to a regional modeling challenge. So I guess either we pick one of the, or we can have multiple categories, and maybe we can set them up in a way they are kind of cumulative. Like you can compare, like, how much does adding this information source help in the compression? We might even consider like doing having libraries of physically based models available to use in your compression without penalty, and see how much the physics knowledge would help. But yeah, those are some ideas, and I had a little detail about the original Hutter Prize. I'm a bit surprised that the length of the compressor is included, and I wonder whether that is correct, because in a way, when you're saying like, what's the description length of my data, the question is, what do I need to regenerate it, right? So if I communicate the data to a receiver, I would give them my compressed file and the decompressor, and that's basically all they need to regenerate the data. So whatever I used for the compressor, I think we should not be penalized by that, but because that's not part of what you need to describe the data, basically. So I think we in this kind of compression contest, maybe just a decompressor and a compressed file would be important.
Okay. Yeah, I don't think I don't recall seeing a distinction between compressor and decompressor. Maybe they're referring to you have to provide two executables. Yeah, I guess they would be different codes. Yeah, that's an interesting detail. Oh, sorry, Hoshin, you're muted.
Maybe the difference here is between storage versus building a model, right? So if all you're doing is storage, you just need to compress the data and provide the decompressor. And you need to know what your language, your algorithm is, what language you're going to operate in. But if you're building a model, you're assuming that the model is the compressor. And if you want to then take it and apply it somewhere else, like a generalization problem, you need the compressor, because that's the thing that's actually doing the work, so to speak.
Yeah.
So I was just going to say one more point is that, okay, in this case for the neural networks, the only part of the compressor that they're including, I guess, because they say, okay, this is available, it's open source or open access, you can get it, it doesn't count, but the parameters count. You have to get the parameters.
Correct.
So they're only counting the size of the parameters.
This is what I was going to say earlier, is you have to choose your language, your vocabulary. You have to choose what you can assume as prior and given, right? And if that's available to everybody, then you can discount that part. It's sort of like we're talking English, so we don't count the number of bits required to store English as a language. We can all take that for granted.
Yeah, so that's kind of the same distinction as what we consider prior knowledge. That's true independently of the data you're trying to model, and actually what's specific to the data.
I mean, this is in a sense what makes it complicated, because it means that your measurement of complexity changes if you upgrade your language, right? It becomes conditional, and your progress of society is partly related to the fact that you're taking that stuff and putting it back into the prior knowledge or the background that everybody can use.
Yeah. Yeah, so that's why I was wondering about the meteorological data. Like, do we say like our objective is prediction in engaged basins, but we consider like remotely sensed weather data to be like the prior knowledge that known that we can start from, and then where we have to demonstrate our understanding, which is equal to compression. We say like how briefly.
I don't think the meteorological data is your prior knowledge, right? It's your understanding of the patterns and so on, and how to use it. That's the prior knowledge. But if I go to another location, I would still have to give you the data, right? Unless when I go to another location, I'm never going to give you the meteorological data again, in which case then it is prior knowledge.
Yeah, so I'm meaning more like in rainfall runoff modeling, then what you start from is the rainfall, and what you have to model is the runoff, right?
But I like your idea of, if you're trying to figure out the nuts and bolts, I like the idea of, if we're saying that the target is streamflow, then you could start with the simplest possible challenge, which would be streamflow. And as you said, then what you're learning is signatures or compressions of streamflow and how those vary. And you kind of did a little bit of that in your paper. But if you're going towards building compressions in the sense that they then represent knowledge of hydrological input state output processes, then we have to say, okay, we have to decide what's the primary thing. You say, okay, I give you rainfall. That's the primary thing. That's prior knowledge. But then I might give you temperature, or I might give you a whole bunch of other things. And the question would be, is how much value does it add for that specific task? And that's very different from building a foundation model, where you would give it all the data you have, and you would have it construct some kind of representation of all of that data, which you could then use as a prior for building a specific model. Yeah.
Yeah. Okay. Yeah.
Yeah.
So if the goal is to, oh, go ahead then.
No. My question on that front is, I guess, are you suggesting two separate competitions? One, like the idea is you're given a string, regardless of what that represents. You just need to compress it. That's the aim. And compressing it means, reducing the, what is it? The, not conditional entropy, marginal entropy. Anyway, reducing the difference between the distributions.
Mm-hmm.
I see what, like, are you saying that, having just say streamflow data, well, a model in that case will look for just signatures that are related in different places, and then by adding and having a separate competition for precipitation, then how does the compression compare on a per bit level?
Mm-hmm.
So will it find efficiencies, between the two? And then I guess, is that what you mean by like by physical laws or processes and links between input and output? Okay. I think
Um,
had his had his hand up for a while.
Sure.
Right.
Just to finish this
Okay.
theme, I rather suspect that there'll be a lot more interest in the rainfall runoff modeling challenge, but it feels like the other one is part of the steps towards it. So there may be people who are interested in the sub challenge, which would be the streamflow signatures. Go ahead, Holger. Sorry, keep you waiting.
Hi, don't worry for waiting. I mean, my question is very boring. And thanks, Dan, for the presentation. It was really interesting. I did compression comparison recently myself, so it was nice to see. I extremely liked your animation. Huh? And I was wondering if you used Manim for doing that.
Yeah, I use Manim. Yeah.
Okay, that's perfect because 2 years ago I was thinking also about Manim maybe doing a project, but I didn't find the right project.
Okay.
And so I just made some first steps. But now looking at your example, I also have an example in my mind where I could really use it. So that's great.
Okay, great. Yeah. Yeah,
So, yeah,
I was worried that I'm just distracting myself and doing this thing when I should be doing other things, but it did help me focus on kind of the inner workings of what this is doing. I haven't mastered anything, but I definitely have a better appreciation after spending time with it.
that's super cool. So you started with Manim from scratch, basically.
Yeah.
Okay. And how long did it take it to make this animation?
You're not allowed to, you're not allowed to ask what I did on my weekend. Yeah, it took a couple days.
Oh, that's okay.
I've played with it before, but never, you get that first step and GPT-4 gets you to the starting line, but as you increase complexity,
So you use
becomes less.
GPT-4 to explain Manim to you.
Yeah, to get me to a starting point. Describe a
that's
scene.
cool.
Yeah,
Okay.
just describe the very basic core of a scene.
Okay.
Display a rectangle, subdivide it, and then from there it becomes a
Okay,
lot
because
harder.
I learned this from the original code, and it took me already at least a day.
Yeah.
Okay, but that's great. So I'm super impressed and looked super nice, and I think I can use it too. Great. So
Great. Thanks.
I liked it a lot.
It's interesting that you mentioned GPT-4 because I just saw today somebody advertising a workshop where they will teach statisticians how to use GPT-4 to help them do their statistical analysis.
Holy shit.
The world is changing.
I mean, scientists already don't know what they actually are doing, but then they will know even less than nothing.
Yep, it's scary. I like the idea of the camels as the foundation because, for example, I mean, we could argue that Freddie's model is the state of the art in terms of predictive power. But at the same time, it's a very huge model in terms of the number of parameters, right? And I don't think that they've done the work yet to see whether they could reduce the size of that model and still preserve the predictive power. So I like the idea of a compression because there are other people out there, like this paper I just reviewed by Danzig for AWR, where he proposes a sort of a hydrologically interpretable model which can be built directly from data. So I think more and more people are going to be trying to do this. And, he's comparing performance to a number of parameters, but it's on this two-dimensional thing. So you don't have a unique way of properly measuring complexity, right?
And coming back to Leila's point about biases, I think that's one of the points that they hit home in this paper is that using this model, that it's not as understood as, say, gzip, what's happening. So using one that's pre-trained, not out of sample, and then looking where it breaks, may provide insight for improving a much more efficient compressor. So taking, finding some component and then incorporating that into a domain-specific compressor, which has a very small, in the order of kilobytes or megabytes program.
So Dan, how long you think before somebody submits a paper to WRR or someone else where they use a large language model and toss the Camels data set in?
That's a good question. I don't know. I'd like this to be part of my my PhD work.
Hmm,
I don't
cool.
know. I think I'm a ways off starting. I have, some obligations with network optimization, but I really hope it supports that question of network optimization.
Hmm.
So I see a link there. That's what I'm currently working on for the BC Hydrometric Service, and maybe I'm dreaming of how this idea of compression can be applied to that.
Dr. Gupta, the paper that you mentioned that you just
Ocean view.
reviewed, is that available to the public yet?
No, not yet. Sorry. It's
Okay.
but it was interesting. He basically, I guess I shouldn't say it's still in review. I'm sure it'll come out pretty soon. But yeah, he was using sort of the analogies to unit hydrographs and differential equations and stuff. So more and more there's going to be stuff coming out. I mean, Luis has done some work using reduced order TM type representations. Luis's paper, I think, is accessible, right, Luis?
Yes, it is.
So Hoshin, is this the paper where they use? Because I was asked to review that paper for it's for AWR, right?
That's correct. Yeah. You
Yeah,
got it.
and
yeah,
yeah, and I think that paper was also submitted to WR because it is online. That manuscript is.
Oh, okay.
And so I
You have the
assume it
link
was
that-
rejected there. And they resubmitted. So I forgot the name of the authors, but I remember looking it up online, going through
Answer.
it. So
DANTZIG. I mean, everybody puts things on archives, so I wouldn't be surprised if we can find it.
oh no, it's there. It's it was submitted originally to WR. Yeah.
Okay, makes sense. Let me see. I could share the name, Joseph. Just
Yeah, that'd be great. Thanks.
yeah, it's generating interpretable rainfall runoff models automatically from data.
Perfect.
Did you find it?
I'm just writing it down first.
Oh, okay, sure. Dancer, sorry. DANTZER, if I did that correctly. Dancer, yeah.
But yeah, it's on Authora, looks like.
Okay, yeah. I mean, to me, it's interesting because as Dan was pointing out, you can build larger and larger and larger models, but at some point you start to get this trade-off where you're getting small amounts of incremental benefit, but the model is becoming huge. And if we're trying to do learning interpretation, then this compression thing obviously becomes an important point. So we're trying to build minimal representations. All right, what time is it then? 7:30. I think I need to go on my bike to the seminar, so it's a day of interesting talks. Luis just put his on there. Anybody wants that one? Yeah. So what's up
Thanks,
next?
everyone.
Yes,
Thanks.
so in our next session, we are going to have Andres Monsalve. He's a PhD student at the University of Texas at El Paso, and he will be discussing fair AI models benchmarks.
Cool.
Yes. And yeah, I'm gonna keep the recording for today, and I'm gonna add the chat so we all have the links that are in the chat right now. Okay.
Perfect.
Thank you, everyone. See you in 3 weeks.
Manuel,
you.
Thanks.
are you
Bye.
there? Just
Bye.
quickly, I'm planning my next trip for mid-August to end of September.
Okay,
We can
good
talk.
to know.
All right. Bye.
Thank you.
Bye-bye.
Bye-bye.